In 1958, a food scientist spent thousands of hours trying to solve one impossible problem: how to make noodles last for months without refrigeration. His solution changed global food culture forever and created a $50 billion industry. Ever wondered what happens inside those mysterious instant noodle factories? Today we're going behind closed factory doors to reveal exactly how modern instant noodle production works. From enormous flour silos to the surprising oil bath that gives these noodles their unique texture. You'll never look at this pantry staple the same way again. And just wait, we'll show you the incredible quality control system that inspects thousands of packages per minute. Ever wonder what makes instant noodles fundamentally different from regular pasta? While that pack of spaghetti in your pantry might seem similar, instant noodles undergo a completely different manufacturing process, starting with a secret first step most companies don't advertise. Regular pasta is basically just flour and water, but when you step inside an instant noodle factory, you'll find they begin with a specialized flour mixture containing an unexpected ingredient. The magic happens when manufacturers add an alkaline salt solution called kansui to ordinary wheat flour. This chemical key transforms everything about the noodles. When kansui mixes with wheat flour, it creates a chemical reaction that gives instant noodles their distinctive bouncy texture and characteristic yellow color. That yellowish tint isn't from artificial coloring or egg yolks as many assume. It's the result of the alkaline solution raising the pH level, causing flavonoid pigments naturally present in the flour to shift toward yellow wavelengths. The scale of these operations is staggering. Inside these factories, massive industrial mixers combine wheat flour, water, salt, and kansui in precise ratios. These mixers aren't just big, they're industrial powerhouses that handle 500-pound batches every few minutes with the precision of a Formula One engine. Like those high-performance machines, these mixers operate with incredible power but require exact calibration to function properly. Quality control at this stage is absolutely critical. I've seen new technicians panic when the dough moisture reads just 0.3% off target, notes a veteran production manager with 20 years experience. Automated systems continuously monitor moisture levels and pH balance throughout mixing. A deviation of just 0.5% in either direction can compromise an entire production run. Too much moisture creates formless dough. Too little produces brittle noodles that crumble in the package. After mixing comes the misleadingly named resting period. There's nothing restful happening inside that dough. The alkaline solution penetrates deep into the wheat proteins, primarily glutenin and gliadin, creating cross-linkages that fundamentally alter their structure. This transformation enables the final product to rehydrate rapidly when you pour hot water into your cup. The chemistry is actually quite similar to what happens in traditional ramen noodle making, a technique with centuries of history in Japan and China. The difference is the scale and precision. What was once a craftsman's art has been industrialized to produce millions of servings daily. Factories maintain climate-controlled environments where the dough rests at precisely 77 to 82 degrees Fahrenheit, 25 to 28 degrees Celsius, ensuring optimal chemical reactions that affect everything from texture to cooking time. The resulting dough has a distinctly different feel than regular pasta dough, slightly more elastic with that subtle yellow hue. Experienced factory workers can identify problems by touch before instruments detect issues. One quality control specialist claims she can feel a moisture discrepancy of less than 1% just by pressing the dough between her fingers, a skill that saved countless production runs from failure. This specialized dough now moves to the next phase, a mechanical process that transforms it at speeds that would make automotive engineers take notice. That specialized dough now faces an engineering marvel that would impress even aerospace technicians. The machinery that shapes your instant noodles maintains tolerances so precise that what happens next transforms a simple mass of dough into thousands of perfectly uniform strands through engineering that would make German automotive manufacturers jealous. The rested dough first enters a gauntlet of massive steel rollers that apply over 5 tons of pressure. These aren't your grandmother's pasta rollers. They're industrial-grade compression systems that gradually transform thick dough slabs into sheets with precise thickness. The dough passes through not just one roller, but a sequential series that methodically reduces thickness with each pass. The consistency maintained across literal tons of production is remarkable. Thickness variations are limited to 0.1 millimeters, about the width of a human hair. This precision matters because even microscopic inconsistencies would lead to uneven cooking when you finally pour hot water into your cup. Thicker sections would remain chewy, quickly, while thinner parts would overcook and disintegrate. Factory engineers don't just install these roller systems and forget about them. The massive steel components require maintenance schedules that rival aircraft engines. Technicians regularly measure roller surfaces using laser micrometers that can detect wear patterns invisible to the human eye. Even a small divot on a roller surface can create ripples in the dough sheet that propagate through thousands of noodle packages. Throughout the rolling process, a network of specialized sensors monitors both thickness and dough density. These readings feed into computerized control systems that make micro adjustments to roller pressure in real time. If moisture content shifts even slightly in a new batch of dough, the system automatically compensates to maintain the target thickness. After achieving the perfect paper-thin sheets, this engineering precision continues seamlessly into the cutting station, a term that hardly does justice to the sophisticated machinery at work. Here, rotating blade assemblies slice through the sheets at speeds reaching 300 cuts per minute. These aren't simple cookie cutters, they're high-precision cutting systems with blades that maintain sharpness measured in microns. What's fascinating is how manufacturers can swap between different noodle styles with minimal downtime. Interchangeable blade sets allow production lines to quickly switch between thin, thick, wavy, or straight noodles, all with the same exacting standards. The difference between styles comes down to specialized cutting heads that impart specific patterns during the slicing process. The tolerances maintained during cutting are measured in hundredths of an inch, precision that would be impressive in watchmaking, let alone mass food production. These tight specifications ensure that each noodle absorbs water at exactly the same rate when cooked. Uneven thickness would result in a frustrating mix of undercooked and mushy noodles in the same package. What's most impressive is the sheer scale and speed of this operation. Modern noodle factories process thousands of pounds of dough per hour, creating millions of individual noodle strands daily. Yet quality control systems can detect and reject individual noodle blocks that don't meet exact weight or dimension specifications. After cutting, the freshly formed noodle blocks move along high-speed conveyor systems at precisely controlled speeds. Factory engineers carefully calculate these conveyor rates to ensure each block spends exactly the right amount of time at each production stage. Even a few seconds of deviation could affect the final product quality. Those meticulously timed conveyor systems are heading toward what might be the most counterintuitive step in the entire process. Why would manufacturers take perfectly cut, raw noodles and deliberately expose them to scorching oil that's hotter than most deep fryers? The answer lies in microscopic architecture that transforms ordinary noodles into instant ones. As the noodle blocks travel forward, they plunge into massive vats of palm oil heated to a blistering 320 degrees Fahrenheit. This 2-minute bath in an industrial deep fryer isn't merely cooking the noodles, it's orchestrating a complete structural transformation at the molecular level. This flash frying process holds the secret to why your instant noodles can sit in your pantry for years without spoiling. When those noodle blocks hit the oil, we witness a dramatic metamorphosis worthy of a sci-fi film. The water molecules trapped inside rapidly vaporize and escape, creating thousands of tiny pores throughout each noodle strand, essentially forming a microscopic honeycomb structure. These micropores serve a crucial purpose. They allow boiling water to penetrate quickly when you prepare them at home, enabling that famous 3-minute cooking time. Instant noodles aren't simply dehydrated like other dried foods. This flash frying process pre-cooks the noodles while engineering their physical structure for rapid rehydration. The transformation is remarkable. Before frying, noodle blocks contain about 30% water content. After their oil bath, that plummets to just 3 to 5%. This radical moisture reduction creates an environment where bacteria and mold can't survive, explaining their impressive shelf life. Modern factories have optimized this frying stage with astonishing precision. Conveyor systems process up to 4,000 noodle blocks every minute, each following an identical path through the oil. Temperature control systems maintain that crucial 320 degrees Fahrenheit with deviations of no more than 1 degree. Even minor temperature fluctuations could result in noodles that won't rehydrate properly or develop inconsistent texture. The engineering challenges are substantial. The frying oil requires continuous filtering to remove starch particles that break off during frying, which would otherwise burn and create off flavors in subsequent batches. Additionally, the oil needs constant circulation to maintain uniform temperature throughout the massive vats, ensuring every noodle block receives identical treatment. This oil frying process comes with trade-offs. trade-offs. Each noodle block absorbs between 15 to 20% of its weight in oil, contributing to that characteristic fatty mouthfeel and higher calorie count. This health consideration has pushed some premium manufacturers toward alternative methods. These high-end producers have developed air drying technology that blasts noodles with superheated air at around 180 degrees Fahrenheit instead of oil submersion. The process takes significantly longer, often 30 minutes versus the standard 2-minute flash fry, but reduces fat content by up to 80%. The trade-off is different texture and higher production costs, which is why most mass-market brands stick with traditional oil frying. As noodles emerge from their oil bath, they've transformed dramatically. What entered as soft, flexible strands now exits as rigid, shelf-stable blocks with that distinctive curved shape we all recognize. The oil coating provides an additional protective barrier against moisture from the air, further extending shelf life. The frying stage creates something remarkable: noodles that are technically already cooked, yet designed for a second cooking process in your kitchen. This dual cooking approach is what made instant noodles revolutionary when Momofuku Ando invented them in 1958. His breakthrough wasn't just creating convenient food, it was engineering a food structure that could reconstitute itself with minimal effort from the consumer. That ingenious noodle structure solves only half the instant meal equation. What happens in your taste buds during those first few spoonfuls involves a sophisticated chemical symphony that food scientists have spent decades perfecting. The flavor packet in your instant noodles contains compounds that can multiply each other's effects by factors of 15, creating tastes that shouldn't be possible from such a small package. Look closely at any instant noodle flavor packet, and you'll find an ingredient list that reads like a chemistry exam. That's no accident. While the package might say chicken flavor or beef flavor, creating those recognizable tastes requires between 20 to 30 different compounds working in precise harmony. This savory broth is actually one of the most scientifically engineered flavor experiences in your kitchen. The foundation of this flavor system is MSG, monosodium glutamate, delivering that distinctive savory punch you instantly recognize. MSG works alongside two powerful allies, disodium inosinate and disodium guanylate. These compounds are taste amplifiers that multiply MSG's effectiveness by 10 to 15 times. Manufacturers can use less MSG while creating stronger flavor impact, similar to how a performance chip in your car can boost horsepower without requiring a larger engine. These enhancers target specific taste receptors on your tongue, essentially reprogramming your perception of flavor with surgical precision. The vegetables in those packets undergo a sophisticated process called explosive puffing, technology originally developed for military rations. Regular dehydrated vegetables take minutes to rehydrate, but these specially processed ingredients absorb water almost instantly in your bowl. The process flash heats vegetables under pressure before rapidly releasing it, causing moisture inside to convert to steam, creating a porous structure that rehydrates in seconds. This same technology allows astronauts to enjoy vegetables in space and soldiers to have quick meals on the battlefield. Temperature sensitivity adds another layer to the engineering. The mixture dissolves completely in 160 degrees Fahrenheit water within just 8 seconds because certain flavors activate at specific temperatures. Some compounds release their rich, savory aromas only within narrow temperature windows. When you smell that first waft of chicken or beef scent rising from your bowl, you're experiencing precisely calibrated flavor release. If the powder dissolves too slowly or at the wrong temperature, the entire flavor profile changes dramatically. Anti-caking agents like silicon dioxide represent another invisible but crucial component. Without these compounds, your flavor packets would turn into solid bricks during storage. These microscopic particles physically prevent flavor crystals from binding together over time, ensuring that when you tear open that packet months later, you get a free-flowing powder rather than a hardened chunk. Even the salt isn't ordinary table salt. Manufacturers use ultrafine crystals with precisely controlled particle sizes to ensure immediate dissolution. The difference between salt crystals measuring 250 versus 400 microns dramatically affects dissolution time and how quickly that salty kick hits your tongue. Color compounds play a psychological role in your noodle experience. Food scientists know that the golden yellow color of chicken broth significantly impacts your perception of flavor. That's why many seasoning packets contain riboflavin or turmeric, not primarily for taste, but to create that visually appetizing golden broth that signals chicken to your brain before you even take your first bite. The color primes your taste buds, making that first slurp more satisfying than the ingredients alone could achieve. While flavor scientists engineer your taste experience, the final frontier in instant noodle production happens after the noodles are cooked and dried. The packaging that seems so ordinary actually represents one of the most precise engineering challenges in food production. Those fragile, flash-fried noodle blocks would arrive at your home as nothing but crumbs without specialized packaging technology that rivals aerospace components in precision. Think about it. How does a brittle noodle block survive being tossed around in shipping containers, stacked on pallets, and sometimes even dropped during handling? The answer lies in packaging that's engineered with tolerances measured in microns rather than millimeters. The biggest enemy is oxygen. Those flash-fried noodles contain oils that begin deteriorating the moment they contact air, creating stale, rancid flavors. Modern factories deploy multi-layer packaging films that combine 3 critical materials in a package less than 0.1 millimeters thick: an outer polypropylene layer providing puncture resistance, a middle aluminum layer creating a 99.9% oxygen barrier, and an inner polyethylene layer allowing for food-safe heat sealing. These packaging machines operate at mind-boggling speeds. A single production line wraps, seals, and cuts up to 300 packages every minute, 5 complete packages every second. The precision is remarkable. Film cutting mechanisms maintain tolerances of 0.5 millimeters, while heat sealing bars hold temperature consistency within 2 degrees Celsius across their entire surface. This mechanical precision works in perfect harmony with rigorous quality control systems. High-speed cameras capture 60 frames per second, inspecting every millimeter for defects invisible to the human eye. They detect wrinkles, seal imperfections, and microscopic holes that would compromise product integrity from factory to your kitchen. The most sophisticated factories employ vacuum testing stations that momentarily place each package in a vacuum chamber. If the package expands even slightly, it indicates a leak, and that package is automatically rejected. Some systems detect holes smaller than a human hair, about 50 microns in diameter. Premium manufacturers employ nitrogen gas flushing systems. Before sealing, they inject pure nitrogen into the package, displacing oxygen molecules. Since nitrogen is inert, it doesn't react with the oils in fried noodles, extending shelf life from months to sometimes over a year while preserving the original flavor profile. This attention to packaging detail extends to sustainability. By maximizing shelf life, manufacturers reduce food waste significantly. The precise material usage minimizes packaging waste, with some factories achieving material efficiency rates of 98.5%. Cup noodles present even more complex challenges. Those foam cups withstand boiling water without leaching chemicals, maintain structural integrity when filled with liquid, and provide the same oxygen barrier properties. The manufacturing process involves molding expanded polystyrene at temperatures exceeding 200 degrees Celsius, creating billions of microscopic air pockets that provide insulation. For flat pillow packs, the packaging film requires precise tensioning during sealing. Too loose, and wrinkles form potential leak points. Too tight, and the brittle noodle block might crack. The tension control systems maintain film tension within 0.2 newtons throughout the entire packaging process, about the force needed to hold up a small paper clip. The entire journey from raw flour to sealed package typically takes less than 30 minutes in modern facilities. Quality checks occur at every stage, with statistical process control systems continuously monitoring dozens of variables to ensure consistency across billions of packages annually. The result? A seemingly simple package that represents an intricate dance of engineering, protecting those noodles until the moment you're ready to enjoy them. From a humble emergency food created in a backyard shed to a global phenomenon consumed 100 billion times annually, instant noodles represent one of food engineering's greatest achievements. Momofuku Ando's innovation wasn't just about creating a tasty meal, but solving food security through determination and ingenuity. Today, his creation feeds millions across 80 countries. When you tear open that familiar package, you're holding decades of innovation, breakthroughs in food preservation, flavor science, and engineering precision that mirror the meticulous design behind automotive performance. If you enjoyed this behind-the-scenes look, hit subscribe for more videos revealing the hidden stories behind everyday products. Every item around you carries its own tale of innovation waiting to be discovered.